All right, welcome back. So we're continuing on with Ruth Hurwitz, and oops, we talked already about getting to this point where we're going to be focused on bibostability. And again, the key thing about Ruth Hurwitz is it allows us to analyze systems and determine stability without actually having to calculate the roots. And the reason why we do that, there are cases when we can't calculate roots of the characteristic equation because we have some variables in here. So we're going to set it up in standard form where we're going to multiply. If we do have the roots, we're going to multiply them all out so that we have these coefficients, A2, A1, A0, and you can keep adding. This term over here is a 1, but it actually doesn't need to be a 1 when we do Ruth Hurwitz. We'll see that in a moment. But let's expand out our poles and zeros. So this is a bunch of math to kind of do a proof for us. But if we have 3 poles and we multiply them out, here's what the expression is going to be like. So s cubed minus the p's added together, multiplied by s squared, plus the pole pairs taking at a pair at a time, p1, p2, p1, p3, p2, p3 times s. And then we subtract from it p1, p2, p3. So let's look at this general pattern and what we mean by that. We see we've got this alternating term here. Can you look and do you see anything inside those expressions? Look at the s squared multiplication, the coefficients. It's p1 plus p2 plus p3, right? I've got a negative over here. If these 3 here, okay, if one of these is actually a negative number, right? So the actual pole is a negative number. It's possible that that could dominate these and make that a positive number, correct? Maybe don't see it so well over here. Let's go all the way over here. P1 times P2 times P3. If any one of these is flip-flopped, meaning instead of, let's say it's instead of a -2, it's a +2, right? When we multiply this together, it should be negative, negative, negative. So 3 negatives with the 4th negative becomes a positive number. If I actually have a root in the right-hand half plane, it's negative, negative, positive. So then I end up with a negative number here, right? Everybody see what I'm trying to do? I'm just trying to explain by multiplying it out based on the positives and the negatives. So what this tells me on this one is if I have one positive number, one positive pole, then this number here is going to end up being a negative number. We don't want that. We want all our poles in the left-hand half plane. So having a 2 over here means that I get a negative number for this last number, which means it's an unstable system. How about over here? We take them 2 at a time. So let's say that this is pole 3. Negative, 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 positive, negative, positive. So it's possible here that these 2 numbers are going to be great enough to result in a negative number over there. And if I have 2 positive numbers, 2 negative numbers, right? So let's say P2 is a negative number or is a negative root. That's a positive number over here. That's okay. But over here, I also have that positive, which could result in a negative number for me. So the thing about Ruth Hurwitz is all of these numbers, all the P1s, P2, and P3, every single number has to be a negative number, or it should live in the left-hand half plane. Otherwise, one of these terms over here is going to end up being a negative number. So the whole thing about the first check you can do, this is called a necessary but insufficient condition, right? Because it could be that there's some criteria here that maybe it's possible that the positives of these is enough to counteract it. But a necessary but insufficient condition is there can be no sign changes in our characteristic equation. All the numbers have to be positive numbers. Okay? That's the thing that we're seeing out here. If you have any negative number, you know that it's going to be an unstable system because I have a negative over here. If they're all positive, it is likely that it's going to be a stable system, but not guaranteed. You need to do more work.
Do you consider
all these numbers in your coefficient. So these all have to be positive. That's called a necessary but insufficient condition. Because as we said right over here, this one we can see, hey, if only one of the poles is negative, P1, P2, or P3 is negative, then I end up with a negative number over here. But what if I have two poles that are negative? Then I can have a positive number there. So that's why it's necessary, but not sufficient. And that's kind of summing over here, right? You can see that when I do this AN1, that's going to be equal to the sum of the negative of the P1s. So that's this term right here. This is the AN1. And then this is the AN2 is the sum of them taking at 2 at a time. They're always going to be a positive number. And then I always go down, down, down. So this is just sort of summarizing it mathematically, okay? But we kind of did it just by explaining it with the previous one. So this is our conclusion. If the system has roots in the right-hand half plane, we can determine if it actually is going to be an unstable system. So let's minimize that. Here's our characteristic equation. We're going to build an array. This is the process for building the array. This is the Routh-Hurwitz array. So we have our characteristic equation all expanded out. The first thing you're going to do is look here. What is the highest order S term? The highest order S term is the name of your first row. Okay, that's the first row. And then to build all these other ones, you're going to subtract 1 from the previous coefficient until you get all the way to S to the 0. So you start out with S to the N, then you go S to the N minus 1, N to the minus 2, minus 3, minus whatever, until you get all the way to S to the 0. Now, here's the next thing. Do you remember how we were here and we saw that this was negative, positive, negative, etc., etc. So what we want to do is, because we swap those around, where we switch, we have a negative, then a positive, then a negative, then a positive. When we build our array, we're going to alternate between coefficients. So if you notice, this is the coefficient associated with that specific row that we're working with, S to the N. Then we skip, because all these are going to have to be the negative row, right? Then we're going to skip and build the positive row. And how do we build the positive row? We're going to start off at the N minus 1, and then we're going to alternate through. And this goes on until we end up with an A to the 0 coefficient, A sub 0 coefficient, so that we have no more. Okay? So now, to do the first 2 rows of your Routh-Hurwitz array, you've just got to identify highest order S term, or the next highest order S term, and then your coefficients are going to alternate. Now to build the next row, we actually have to do calculations. And how do you do the calculations? This is where it gets a little tricky. You're going to do B1 here, and B1 is going to be determined by calculating the determinant of that row, or of the previous 2 rows. And then you're going to take the negative term over here. So does anybody know what the determinant of this first B1 term is? Do you know how to calculate determinants? Have you done that in linear algebra? Yep, keep going.
Minus bracket.
Not minus, right? Isn't it multiply? Yeah, to find the determinant of a 2x2 matrix, you take the diagonal left to right, and then you subtract it from the diagonal right to left. Okay? And then you have the negative term up front. That's B1. Now, to get to B2, you're still going to use the determinant approach, but now it's going to be modified a little bit. So I'm going to use this one here, and then I have to skip the term that's above it and go from there. So the way that I describe how to calculate these, the determinant, is it's always going to be the first row or first column, and then the second column is always the two elements above that are in the column just to that right of the coefficient I'm trying to solve for. So if you see, my B2 is negative 1 over an minus 1 times the determinant, still the first row, right? An over an minus 1. But now it's an minus 4 over an minus 5. And then B3, if I have it, I would be using that as my second row. I still always use that one. It's always the first row or first column. But the second one is going to be the column that's always just to the right of the column that you're trying to calculate that coefficient. Now, I'll go on until I'm out of coefficients. If I'm done with my B's, then I move on to my C's. And all I do is I move down one row. So to calculate my C1, whoops, I went a little too far. I'm going to move down single row and do the same calculation over again. Okay. And so essentially what it's doing is it's kind of doing that process where we have P1, P2, P3, or P1, P2 times P2, P3 times P1, P3. It's doing it with this determinant approach. And it's doing this negative, it's putting this negative up front because it's actually trying to calculate or keep that negative going along. And then you go all the way down until you only have one element in your final row. And that element right here, that's how you can check if your work is correct, should always be that A0 term.
Oh, the N1 will always be equal to A0.
Yep. So the rule for Ruth-Hurwitz is if you have any sign changes, you've got a pole in the right-hand half plane. The number of sign changes you have indicates the number of poles in the right-hand half plane. Okay? Makes sense? We'll do some practice problems for sure, but.
Yeah, and also the like so you said A N and then A N the second row is A N minus 1 and then third row is B1.
Yep.
Then C1.
Yep.
And left one after that.
That'd be D1 if you have to keep calculating it.
But then what will determine how far down you go?
Say that again.
What will determine how far down?
Right here. That determines when you stop. When you get to the S to the 0, you're done. You can't go beyond S to the 0. There are no more coefficients to evaluate.
But then we will always have A N and A N minus 1.
Right.
Those two always.
Yep.
C1, C1, C1.
Yes. Yeah. So generally speaking, you only do Ruth-Hurwitz if you have an S cubed or greater. Because with S squared, you can just use a quadratic equation and say, hey, what are my roots of this? And you can leave it based on a variable. So you can actually do the math with an S squared term pretty easy. But it's once you get to S cubed and above, you can't do the math so well. So that's when you have to use the Ruth-Hurwitz approach to do it. Okay. All right, here's an example. So first thing I realize is I focus on my characteristic equation. S cubed plus S squared plus 2S plus 8. And then we just write over here what our terms are going to be. So step number 1, I identify the highest S coefficient. In this case, it's S cubed. So I'm going to build my Routh-Hurwitz array starting with row S cubed. So here's my S cubed. Then I go to S squared, right? N minus 1, S to the 1, and S to the 0. And then I stop. And now I'm just going to go ahead and start stuffing in my coefficients based on what I have. So this is the 1. So that becomes my A1. I skip the S squared term, right? Because I'm trying to make sure that I balance out those pluses and minuses. So my 2 moves over here. This is also a 1. That becomes A1. And that's A0. I certainly could continue to add coefficients going in this direction, but what are the coefficients I have over here? It would have to be plus some number, we'll call it A5, times S to the minus 1, right? Which you should never have a 1 over S in your characteristic equation. Why should you never have a 1 over S in your characteristic equation? It's possibly integration, which that could be, but why do we never have a plus 1 over S? It's easier than that answer. What is the core rule that I have in this class when you're doing block diagrams and all that stuff? What's that? No fractions within fractions, right? So if I have a plus 1 over S over here, what am I going to do? I'm going to multiply that by S, right? And move the S into the numerator, correct? So I don't have any S to the minus 1 terms because I've moved those up into the numerator by doing common denominators and whatnot. But if I did, which I wouldn't, you would add those over here. But in this case, we don't have any, so we're just going to put zeros. So if we did the determinant approach, where we're trying to solve for B2 over here, you can see that you have a bunch of zeros. So you actually don't have to do any calculations. All right. So here are our numbers. 1, 2, 1, 8. Pausing for station identification to make sure you all see where those numbers came from. Make sense? Does it make sense? Right now, we're just doing the algorithm. We haven't done any calculations yet. We're just doing the initial setup so that we have our Routh-Hurwitz array and we're ready to start doing calculations.
So this is just some procedure to basically memorize.
Yes, but it's all based on here, right? It's making sure that we meet this pattern. If we want all our poles to be in the left-hand half plane, eventually what we know is that all these coefficients have to be positive numbers, right? That's a necessary but insufficient condition. The other thing that we have to do is if we do get any sign changes when we do some calculations, this is a little bit more math, we see that these, you can see alternate, we have to cancel those terms out. So that's why we get to here to do this procedure. That's just the Routh-Hurwitz procedure.
So you, instead of having 8, we have minus 8 already. So
If this is minus 8, and I said, tell me if there are any poles in the right-hand half plane, you'd say, I don't even have to do the problem.
Yeah.
Because I have a minus 8. And I already know that I have at least one pole in the right-hand half plane. If I said, tell me how many poles are in the right-hand half plane, then you'd have to use the Ruth Hurwitz approach. But if one is just a stability check, there's nothing you can do to make a -8 a positive number. You know, just can't be done. So you just roll with it as best as you can. Okay, let's do B1. Here's B1. Substitute in the coefficients. You can see I want A3, A2, A1, A0. That's going to be in my actual determinant. And let's check and see if this makes sense. So I've got the determinant approach, right? Which is, and then also I forgot, I should have mentioned, you're also always going to divide by that term there. So if you're calculating B1, it's always going to be the term just above it in the same row that you're going to calculate. Okay. So it's always that specific term, that A2 term. So you have to multiply by -1 over a number. The number that you're multiplying it by is always going to be, so we do the determinant here, it's always going to be that coefficient there.
It's always going to be eight.
Always going to be A2, or if you move down to the next row, it'd be B1. And I think, let's see, did I? Yeah, so you can see it over here. See, it's A to the n-1, A to the n-1. Everybody see that? I'm trying to remember from linear algebra, it's been too many years for me, but if I determine the inverse of a matrix, I have to do the determinant, but then I have to do method of cofactors, which is, can't remember that off the top of my head. Anybody remember how to do method of cofactors? To do determinant, to actually solve for the inverse of a matrix? No? What's that?
You don't have to do it.
You don't have to do it, but there's this A to the n-1. There's a way to get that if you look at what's called method of cofactors. And if you were to try to solve for an inverse of a matrix by hand, that's how you would do it. Anybody here taking 258 or the linear algebra one? Do you remember method of cofactors? Yeah. Do you remember how to calculate the inverse of a matrix?
We did matrix stuff, but we didn't do like much hand stuff. It was just kind of
Put in your calculator.
Put these equations into matrix and just solve.
I know.
Something that's multiplied by. But that like it's like the T here that goes a little back and
Well, you end up to get an inverse of a matrix, that's what you're doing. But to do it sort of with a procedure, you actually do what's called the method of the cofactors, and it's like you cancel the row and the column. So if you're trying to solve for, I believe that's called method of cofactors. So if you're trying to solve for this coefficient here, you cancel this row and this column, and then you're left with a 4. But it's not just a 4. You have to have the negative of the number, and then I think you have to divide by the determinant, right?
Oh yeah, there's some. Yeah.
That ringing a bell?
Yeah, I don't think you have to call that.
Okay. I thought that was called method of cofactors to do it, but that's the automated approach. But you can see it's a lot of work to get there.
Yeah.
But I believe the reason where this comes from is derived from the method of cofactors. But I've never seen the full derivation for it. So anyway, if you want to get into linear algebra, that's one of the things I would tell people. If you have any interest at all in going to graduate school in engineering, you should always take the linear algebra course, because so much of graduate school is just trying to make things easier, and just dealing with systems that are really complex. And so I would recommend you take MAT-262, the actual linear algebra course. I would suggest taking that course over the differential equations and linear algebra course. That's just my opinion. But I took the linear algebra course and I thought it was great. I think that really helped me out in grad school. Anyway, I think they still offer MAT-262, I believe. So.
But now There's not calculators, best calculator that we got.
Yeah, but a lot of it, again, remember, we can do Ruth Hurwitz. We don't need to do it if we know all the terms, but if you have to design something, you have variables that you're trying to specify. So you can't just use your calculator, right? Or maybe you can do it symbolically. I don't know. I don't think you can, but who knows, right? The world is changing. Maybe it's easier, but anyway, let's check that this determinant approach is what we expect. So we have -1 over 1. And so we're going to go 8 minus 2, because it's 8 times 1 minus 2 times 1. So 8 minus 2 is 6. Then we multiply by the -1 up front, and we end up with -6. Okay. Now we'll move on to B2. B2, we're going to use the first column. And we're going to use 1 just to the right of it. Now, this is an easy one because we've got 2 zeros here. And when we do that determinant where we cross multiply and subtract, we're always going to end up with 0. So here's the other thing too. You can see that when you end up, if you have a column of zeros, the next coefficient that you calculate over here, that's always going to be equal to 0. Not guaranteed to be, but if you have a column of zeros here, this is 0. If you do have a number in here, it would be over here, and B2 would not necessarily be 0. Okay, so it just depends if it's s cubed or s to the 4th, whether you would have that extra coefficient in here. So this B2 here may or may not be 0, but C2 is always going to be equal to 0. Because as we said, the only coefficient that you have in your s to the 1 row should be your A0 coefficient, which is equal to 8. All right, so we see that we've got our B2 is equal to 0, and we're done. There's no more point in calculating B3, B4, because they're all zeros. Now we're going to move down a row and calculate C1. So C1 is going to be, try to clean this up because it's kind of getting messy. So my C1 is now going to be using these coefficients to calculate for its determinant. So C1 is going to be equal to the determinant of here divided by B1, or multiplied by 1 over B1 because it's a vector. And then I take the negative of that. So I can see that my C1, -1 divided by B1 times A2, which is here. That's A2, A0, B1, B2. When I put that in here, I get -1 over -6, because the -6 here is what we calculated for B1. So I have 0 minus a -48, which is +48. And then I multiply that 48 by 1/6, and I get 8. Did my results check out okay? What was the one rule that I said you can check your work? Yeah, this last term right here should be equal to A0. So the question is, how many sign changes in that first column? How many changes in sign? Just 1 or 2?
And that's what you find. Yeah, like if you go for plus, minus, and go to plus of 1 sign change, minus plus 2 sign change.
I'll ask it by I'll answer your question by asking a question. This is a positive number. How many sign changes?
No sign.
How many sign changes? How many sign changes?
Twice.
So what do you mean by how I define it? There's no definition. It just look, does it change sign or not? I didn't ask you how many negative numbers. That would have been the response you wanted. I said how many sign changes. I was very careful of the verb or the language I used. because I have two sign changes, not two negative signs, two sign changes, I have two poles in the right-hand half plane. All right, put in MATLAB or calculator. I'm just gonna put the roots, 1128. So I get -2 plus j and 0.5 plus or minus j 1.9, whatever. So how many poles are in the right-hand half plane? Does this indicate 2? Which 2 are in the right-hand half plane? 0.5 plus or minus. Okay, you can check that in MATLAB. First off, we'll do the roots, if I can ever find where MATLAB is. So roots, we'll just do it again, just so everybody can see it. 1, 1. Was it 6 and 8? Or 2 and 8? Let me just double check. Okay. And then if I do my transfer function, and I'm going to pass it my 1, 1. And then I'm going to do my 1. Let's see. Remember their function PZ map, pole zero map? Let's check and see if that's what we end up getting. If it wakes up.
So the number of sign change indicates the number of poles.
In the first column indicates the number of poles in the right-hand half plane. So, anybody see? This is odd. This is showing
Oh,
oh yeah, there's one at -2. There's a 0 at -1. But look where I am at the j omega axis. So right here, right? You can see it's the real, it's the 0. And I can see I've got one here. And I've got one here.
it's two. Whoa, two.
Those two, which two?
In the right hand,
These two, there's one up here and one down here.
in the right side.
Well, what does 0 correspond to right here? That's when the real part equals 0, right? So this is the j omega axis right here. So everything over here is in the left-hand half plane. Everything over here is in the right-hand half plane. So those are in the right-hand half plane. Pardon?
It's not level.
Yeah, because if we have two poles, okay, so we have S, so what we end up with for our expression is S plus 2, and this becomes S minus 0.5 plus J 1.94. So when we go back into the time domain, we know that this is going to be A e to the minus 2t plus this right here is going to be B e to the 0.5t minus J 1.94 t, right? And this becomes plus C e to the positive 0.5 t plus J 1.94 t. What happens as time increases? They increase too. Yep.
Which means it's unstable.
Comes unstable.
But then just by when if you didn't match that, that's why you know there's 2, 4. Well, oh.
Right there tells me there are two poles in the right-hand half plane.
If there was no sign change, means
If there are no sign changes, then they're all in the left-hand
they
depth.
have been.
Yeah. There are some special conditions that we may have some of the J omega access, and we'll see that in a bit. Oh, I included the pole zero map, so you can always, shouldn't have done that extra step. All right, 5 minutes, your turn. Help me out. This one, you're gonna see also that your C2 term is not necessarily gonna be 0. Or not C2, B2 term will not necessarily be 0. You'll see here in a second. One more minute. Okay. What'd you get? What's B1 equal to? -7? Anybody get -7 for B1? Okay. So I got 2. -7. How about B2? 10? Here's 10. Do we calculate B3? No. One thing I didn't mention, it might be helpful. If you look over here, you can see in the S cubed row, you don't have an even number of coefficients or the same coefficients as the S4. So if you want, if you're unsure what to do, just put a 0 in there. You can just specify a 0. You can see that that's over here, but if you don't have it, you can just include it at a later date and time. So if we move over and calculate B3, we know that B3 is just going to be 0. So there's no point in calculating it. So now we're going to move on to C1. What'd you get for C1? (45/7). Yep. That's good. C2 should be equal to 0. And then D1, I don't even need to calculate D1, but it's always a good idea to calculate D1 just to make sure you've got the same value, right? If you didn't get 10, then you might have made a mistake someplace. Well, you definitely have made a mistake someplace there. All right, so how many poles in the right-hand half plane? 2. Why? Because there are 2 sign changes. So let's check. Here are the roots. Do you see 2? Do you see 2 poles in the right-hand half plane? If you aren't sure by seeing it that way, you can always do our transfer function, our approach. So we'll do a transfer function. And in the numerator, we're just going to pick a coefficient of 1. We'll just say that it's 1. We have to have something in the numerator. Otherwise, it's not going to work. And in the denominator, we have 2, 1, 3, 5, 10. So 2, 1, 3, 5, 10. Is that the correct expression? At least the characteristic equation's there. So now we do PZ map. And bring up the plot. And how many poles in the right-hand half plane? 2 and only 2. You can see that here. And I guess I'll do the annotate. Those are in the right hand. Say that again? It just tells you the number of poles in the right-hand half plane. Yep. Okay, but again, why is that important to us? Well, what if I told you that's not a number, but K? How would you put that into MATLAB or your calculator? You can't, right? How can it calculate the roots if you have a variable? So we'll see how we'll calculate that. So let's do a case where we have A or alpha. So how do you like this expression? Should we choose alpha to minimize problems? Which means if we can, make sure the system is stable. Sometimes there's nothing you can do to alpha. So let's do this. Let's do this one by hand. So we'll do S4, S3, S2, S1, S0. And then we have 2, 3, 5, 1. Oh, wait a minute, I skipped. I said 5. It should be alpha. 1, 5, and 0. So this coefficient over here, our B1, is going to be equal to -1 over 1 times the determinant, 2, 1, 3, 5, which we determined this earlier, we said was equal to 7. Correct? Now B2, this is going to be equal to the determinant, so it's -1 over 1 times 2 alpha, 1, 0. So we're going to have 2 times 0, which is 0, minus alpha times 1, which is minus alpha, but then I cancel that out, that becomes alpha. So what I end up with over here is I have 7 and alpha, correct? Do I have to do anything with alpha yet? No, because I haven't had any sign changes. These are all positive, right? Let's go to C1. Move down a row, so I have -1 over 7 times 1, 5, 7, and alpha. And that's going to be equal to alpha minus 35, correct? So alpha minus 35 divided by 7. And don't forget, I need the negative up front of it. All right, so this becomes alpha minus 35 over 7. And we can do the calculation if we want, but we know that that's alpha. So how do I minimize problems? Say that again? Oh, should have a negative sign here. Yes, thank you. So how do I minimize problems? Yes, sir. So if alpha minus 35 negative is greater than or equal to 0, I'm minimizing problems. It's essentially what you said, right? Everybody agree with that?
Is there a problem with this equal 0 there?
Not necessarily.
Please consider that possible.
Well, I'm only caring about if there are any poles in the right-hand half plane. There is a way to check if it's on the j omega axis, but we'll get into that in a little bit. So how do I check this? How do I solve for alpha? Let's see if we're really good with algebra. What should you do first?
And put this negative signs like 35.
If alpha becomes greater than 35, right, then this becomes a positive number, which makes this a negative number, correct?
Oh,
This has to be positive. The negative's up front there, right? So alpha had better be less than or equal to 35. Otherwise, what comes in here is a negative number. I mean, it's a positive number. And then when you multiply by the negative, you end up with a sign change there. So am I done? As long as alpha is less than 35?
when you solve it out, it says that alpha is greater.
No, I moved the alpha to the other side, right? Oh yeah, alpha is greater than, oh, that's right. So alpha has to be greater than 35. So what happened here?
You have the sun. Well,
Here?
put the negative sign inside. There's a negative sign. Put it in the slide.
I made a mistake where?
I think it's just in the third that last bit. Right in the top there. Maybe that right.
But we know we want this term, we want it to stay positive number, right? So here's, I think the mistake was made.
That's right.
when you get rid of the negative sign,
Yes.
you have to swap the equality. You do it that way. Right? So that's when I said, how good are you at algebra? Once you start monkeying with negative signs in your equalities, now you got to start swapping things around. So my recommendation is not to distribute it. It actually is to multiply both sides by the -1. And when you do that, you just have to remember, now it's no longer a greater than, it becomes a less than. Okay. So is alpha being less than 35, less than equal to 35, good?
Yep.
Everybody agree? Can I raise my hand and say I don't agree? Because I said any sign change in the positive, the first column is okay, right? So can I pick alpha equal to -74 or 54? Is that okay? It meets this criteria. It's less than 35. Won't I have a negative here? So there's two requirements. Number one, number two, because of this row. Make sense? Don't make sense? Any sign change means a pole in the right-hand half plane. If we just made this one requirement, then alpha is less than or equal to 35, means we have anything below 35, including all the negative numbers. But over here, a negative number means we have a sign change in that first column, which would not allow. So you can check it, right? Let's go back to here, our MATLAB, and let's do roots of, so we had 2, 1, 3, 5, and let's pick 34. Okay, that's less than 35, right? Whoops, 2, 1. Wait a second. Did I do that wrong? 2, 1, 3, 5, 34. Why am I getting? I'm getting positive, even though did I make a mistake here? I don't think so, but it's giving me a positive number. Alpha minus 35, so 34, -1/7. I'm not sure why this isn't working out. It works with this. Well, let's check this one. Let's check. That's,
If you had 10, that still leave us.
yeah, we had two sign changes. Is this a -7 or is this +7? Maybe I made a mistake here. Oh yeah, this should be negative. So yeah.
Oh, yeah. So
So I forgot the negative. So that there's no matter what, there's nothing I can do to alpha to make it a positive number. There we go. That makes sense now. So if this was a positive number, then I would be okay. But since it's a negative number, there's nothing I can do with alpha to make it so that it's going to result in a stable system. So you have to start from scratch. You have to start rebuilding your system. All right. So what happens if we have a 0 in one of these columns here? We shouldn't have a 0 here, because that would mean you don't actually have a high order S term. So you could have a 0 here. What happens if you have a 0 here? That would be plus 0 s cubed. Close. If you are missing a coefficient in any of these, and what I mean is s to the 4th plus s cubed plus s to the 1 plus 10, or s to the 4th plus s squared plus s1 plus 10. If I'm missing one of the coefficients, meaning I don't have an s squared here, right? I don't have an s cubed here. It by default means it will be an unstable system. So if one of the coefficient vanishes or is missing, it's unstable. Nothing you can do. Yep, nothing you can do. So if you had a 0 here, you can't even do the Ruth Hurwitz approach because you're going to end up with an infinite number when you get there. Okay? So as long as you have those two necessary but insufficient conditions, which is number 1, all coefficients are positive. And number 2, no coefficient equals 0, then you can actually do the Ruth Hurwitz. If either of those apply, then you don't need to do the Ruth Hurwitz approach. You're dead out of luck. Now, it's possible that you could end up with a 0 over here, right, in that first column. And the problem with that is if we have a 0, then one of these terms, let's call it the C1 term, when you multiply by the -1 over that first column coefficient, you're going to end up with a 0. So this is always going to be equal to infinity, right? Which we can't handle that. We can't deal with that because if we continue to use those coefficients moving forward, we're just going to have infinities minus infinities. It's not going to work. So if you have a 0 in that first column, that's beyond the first 2 rows, here's what we need to do. This is the problem. This is another problem when we have a row of zeros. We'll see how to deal with that later. So we only want, so here's the key thing. This is highlighted. Make sure you highlight this in your slides or whatever. I only have a 0 in the first column. Okay? So I'm doing my work and I end up with just a 0 in the first column. All the other coefficients in that row are non-zero. Then I'm going to substitute 0 with a variable. I'm going to call it E. And E is a very, very small, infinitesimally small number, but it's not 0. Okay? And that's going to allow us to do our calculations and complete the table. So we're going to complete the table with our variable, E. And then when we're done our work, we're going to let E approach a really small number and then see if we get any sign changes. So kind of reiterating, if you have a Z only in the first column, replace it with the variable E, continue your work, and then at the end, when you do your evaluation checking for sign changes, check and see if you have any sign changes by allowing E to go very, very small, basically go to 0, but not act 0, so you can look and see what the results are. All right, so let's do this example. S to the 5th, 2s to the 4th, 2s cubed plus 4s squared plus 11s plus 10. What's the highest row that we're going to have? S to the 5th. So we build our S to the 5th, S to the 4th, S cubed, S squared, S to the 1, and S to the 0. Now we're going to start populating our first 2 rows with our coefficients from our characteristic equation. 1, skip a number, 2, skip a number, 11, and we're done. We don't have any more to go. Then we move to our S4 row, and sometimes I find it helpful to do this. So it kind of screams at you if you want to do that little thing. So that's my first row. So this is S5, and then S4, That Y kind of screams at you saying which terms are you going to use? And this is my S4 row. Now I got to calculate B1 by doing the determinant there. Uh-oh, I end up with a 0 there. Now, I said to replace it with a 0, but technically, I should wait to replace it with a 0 until I check what B2 is. So B2, I really should, before I do this first, so I'm going to wait, and I'm going to check and see what B2 is. B is a non-zero number. B is 6. So now I would go back in and update B1 and make it a 0. So my first step would be, I'm going to write 0, then I'm going to do B2, and now I've actually got a non-zero number in B2, so I'm going to cancel this out and replace that with E. So I'm only going to do that after I've checked to make sure that I don't have a row of zeros here. Because if I have a row of zeros, there's a different approach. I can't use this little E term approach. So here's my E in 6. Now I'm going to go ahead and calculate C1, but using that term E, the variable E, instead of 0. So now I got to do a little more math. 4E minus 12 divided by E. I can still do the calculation. It may not be pretty, but I can still do the calculation. And C2, now I include my E term in there. It's going to be a little bit easier. So now I'm going to go ahead and replace that. 4E minus 12 over E divided by 10. And then I'm going to continue on. I'm going to do D. This is when it gets really ugly, right? I got a lot of math to get there from here. But if you do the math, you end up with 6 e to the minus 6 minus 5e squared, and that's divided by 2e minus 6. And then I can certainly check E1, but it's a mess. So at this point, maybe you don't want to check it. Maybe you just copy 10. All right. So now I've got to go ahead and do my calculation. If I allow E to approach a very small number, let's call it 0, what happens to here? It's negative 12 divided by a really small number, right? Which is minus infinity. So I've got a positive. I'm going to assume that E approaches 0 from a positive number. So those are 3 positives. Now I can see that I've got a negative number over here. Now I'm going to go ahead and do this. So 6. So remember, this E term is approaching 0, and you have an E squared over here. So this essentially is going to go to 0, right? Because you have E squared in the numerator. If you do a limit function, you have 5E squared is going to approach 0 faster than 2E in the denominator. So you're going to have 6. That's a positive number. And this is 10. So how many sign changes? 2 sign changes. Here and here. Exactly what we had. Does everybody understand what I did here? Because this usually blows people's minds a little bit. This one, hopefully, this one you can see that this just becomes minus 12 over E or minus 12 over 0. This one's a harder one to see. But the only way that I do it is I just do a limit as E approaches 0, 5E squared over 2E minus 6. If you remember from limit functions, when you're using your variable, all you really focus on is the E terms, the highest order E terms. So you end up with E squared over E, limit function. That just becomes E, right? E squared divided by E is just E. So now you can see that as you do the limit, as E approaches 0, it just becomes 0. So that's how that term canceled out. That's usually what causes people the most confusion when doing these, okay? So if you have E squareds in there, just use your limit function, and then just, again, use your approaches, which is just whatever the highest order term is in the numerator, divided by the highest order term in the denominator, and that'll tell you if it goes to 0 or infinity. It's going to go to 0 or infinity. That's what it is. So 2 sign changes. Matches our results.
And then, now also, so that we could add any zero on in the CD, right?
Yeah, if you have any zeros in here,
Oh, wait.
it's an unstable system. You have at least one pole in the right hand half.
But then now, what if the jump, so it's S5, and then there's no S4, go at the same time, S3.
So if this was zero,
Yeah, I mean, you don't have,
then it's an unstable system. So what we're doing Ruth Hurwitz for, we're actually don't need it really to check to see if the system is stable or not. We're going to use this for design. And so the idea is that, well, if I'm using it for this design, but the system is always unstable no matter what I do. Remember the example we did over here, but I screwed up the -7. I forgot, look, the -7 over here. There's nothing I can do to alpha to make this system positive, make it a stable system. So why would I even do any work? I have to go back to the drawing board and modify my system. So if you have any coefficient that vanishes, then you're dead in the water. Don't even bother starting. Okay. Shall we check it in MATLAB? Works pretty well. Let's do a quick one. So our roots are going to be, whoop. So the root are going to be 1, 2, 2, 4, 11, and 10. Do I have that correct? 1, 2, 2, 4, 11, and 10.
Yeah.
Should have 2 roots in the right-hand half plane. You can see that I've got a positive 0.755 plus J. If you don't like it, you can always go back and just do this every time. It works really well. And then we do our 1, 2, 2, 4, 11, and 10. Close that. And then PZ map it. No way your calculators can beat that, right? That the Inspire calculators can't do. That's the new fancy TI-89, right? That's the next level. There's no PZ map feature built into that, right? Told you I'd finally win. There you go. You can see the right here. Why don't you go? So turn that off. Right here is the J omega axis. And I have here. And I have here, which are in the right-hand half plane. And we said that there are 2 poles in the right-hand half plane, which we just verified with it. Question?
Yeah, we go the,
Yeah, let me just clear this. How are we doing for time? We're running out of time, but we will.
yeah, so you assume that the E is positive, coming from the,
I'm coming from there, yeah, because if I assume that it's a negative number going to 0, then it's always going to be an unstable system, right? So if I see that I've got an E here, there's a 0, then it's always going to be, if I'm assuming that it's no matter what, it's unstable. So you assume that you have a chance of being a stable system. So we'll take our limit function and approach 0 going from positive, not negative.
and then also we said that since for B1 is 0, but then you not put the 0, you wait to find B2 first.
Yes, so step 1 was we calculate, so we got to go all the way back here. So this, I said, wait, don't do anything yet. Don't replace it by E. Put the 0 in here. Because then you want to calculate B2. If B2 is also a 0, then there's a different approach that we have to take. But if B2 is not a 0, then you go back in here and you cross out that 0 and you replace it with E.
Does it apply for any if we find that this corresponds C1 is 0, you have to wait and find C2.
Yep. Yep. Most of the time, when we do our work, we're gonna end up with a row of zeros here. That's the other thing, we're kind of jumping ahead a little bit, but this is just crazy math. But you will only have a row of zeros in S2, S4, S6, S8. You can never have a row of zeros in an odd row. It'll make more sense when we cover it, but you can never have a row of zeros in an odd row. Yes, sir.
Are those B1, C1, C2? Do those mean anything? Or are they just numbers?
They're just numbers in the calculation. They don't really correspond to anything going back to our original, like you can't pull the roots out of that. So you can't get there from here. It would be great if they could, but you can't get any information out. Okay? So, I mean, you can see over here, if we allow E to be less than 0, right, to approach from the negative number, then you've got a negative over here. So it's always going to be an unstable system, right? So you don't have much of a chance there. Here's our check. Here's our pole 0 map. This one has S+1, but that it doesn't really matter what the numerator is. We really only care what the denominator is. How's my time? I don't think we have enough time to cover this. So any questions on this material?
You think we'd actually use this, or we just use something like MATLAB?
Well, like I said, if you got to this point here, where this equation, this number is K, how would you use MATLAB? Can't solve for the roots. So the only reason why we teach this stuff still is because you're using it to design something. You're actually trying to specify what that value of K can be so that you can tweak your system, but still have a stable result. Okay, any questions? Right, that's all I had. Hope you have a great day. And I will talk to you later. Take care, everyone.
Thank you, Paul. Thanks, Paul. See you later.
Say that again?